in person, the same thing that you see on Teams. So I have like a writing pad here, and I'll display that writing pad kind of on the wall behind me to do the lectures. And I'll also display the writing pad on Teams, sharing my screen. So everyone's going to get the same information and same experience. Hopefully you guys have all checked out the Canvas. I've used Blackboard in the past. This will be the first quarter I'm using Canvas, but I'll upload all the course materials to Canvas. So lecture notes that I personally make, I make them in PowerPoint and I distribute them to you guys so you can follow along as I lecture with those materials. I think it's useful if people like to have a guide to go with. They can follow along with those PowerPoint slides. Otherwise, if you like to take notes traditionally by hand, that's usually how I'll do things. So I'll keep grades up to date. I'll post homeworks there. I'll post simulations there, all on Canvas, lecture notes, all that sort of stuff will be done on Canvas. Okay. I also have a YouTube page where I'm going to upload the lectures. I don't want to upload the lectures to Canvas just for space reasons. So I have a YouTube page. The link to that is on the welcome moniker for Canvas. So right when you log into our page for Canvas, you should see the link to the YouTube page there. Otherwise, just Google Kevin Hart. I'm sure it'll pop right. That's the joke. Okay, I got one laugh. Okay, so that's good. Okay, so not a really deep day today. I do want to go over the syllabus. I know it's like syllabus week or syllabus day for everybody. So I do want to go over the syllabus, which is posted on Canvas. And then maybe we'll have a quick introduction to mechanics. You know, what is mechanics? What are we kind of trying to achieve with mechanics? And what are you going to sort of learn this upcoming quarter? Yes, rawr, new materials. Let's go ahead and get the syllabus in here and we'll talk it over. Okay. Zoom in a little bit here. All right, so here we are. The syllabus available on Canvas, like I said. Your instructor, Dr. Kevin Hart, that's me. I'm not as funny as a comedian, but I try. All right. My office is in the science building. It's right across from the foundry. If any of you guys been kind of at the foundry, the material science area of the building, right across the hall from there. I can't really have students in my office hours, but if you want to knock on the window and wave, that would be nice. My phone number is there. I will answer the phone if you call me. I know students don't really like to do that, but I will answer. And we can talk about mechanics or your favorite scary movie if you'd like. Beetlejuice, my favorite. No, I'm just kidding. That one's not very good. Okay, my email address is there. If you want to get a hold of me, that's probably your best bet. I'm pretty good about getting back pretty quickly. I have office hours every single day, 8 to 9:30. You don't have to worry about, is it Monday, is it Thursday, is it whatever. Every day, 8 to 9:30, every day. Okay, and I hold those office hours on Microsoft Teams. So pop in there anytime, 8 to 9:30 message. You should have all been invited to my office hours team. If you haven't, please send me an email and I will invite you to that team. And just pop in if you have struggles. I really encourage you to do that, right? Class meetings are going to be in 310 Dirks. Like I said, it's going to be this hybrid model. I have the eligibility for people by last name here. Tuesdays and Thursdays, those people can come in person. Wednesday through Friday, that other group can come. But based on the attendance today, I think pretty much anyone could come anytime they wanted and we wouldn't fill up this room. So if you want to come any day, I think it would probably be okay. Otherwise, if you're the bashful type or you prefer the online world because of hashtag COVID life, you can stay at home and be safe as well. That's fine with me. The textbook for the class, I really encourage you to get this. You'll use this not only for this class, but the next mechanics class as well, is this Hibbler book. Really quite a good book, actually. We just made a switch to this book and actually kind of like the newer book. So recommend getting that, although I do make all the PowerPoint slides myself if you go through the class without the book. Okay, course description. I think some of you kind of already know what this class is about, but the basic idea here is that we're going to study forces on objects that are not in motion. Equivalent force couple systems, free body diagrams, all the good stuff. It's probably maybe one of your first forays into engineering classes. So start to see some engineering diagrams, some forces on things. And I think this is kind of the exciting time where you actually are starting to learn how to be an engineer. So excited to take this adventure with you guys, even though it's kind of in this strange atmosphere. All right, so here are your learning outcomes. You can sort of read those at your own pace. These are the same learning outcomes that you'll see in the course catalog online. All right, prereqs, got to have calc, got to have 190. All right, so 190 is a prerequisite here because we're going to use MATLAB to do some simulation assignments this quarter. So more on that in just a second. We're going to talk about scalars, vectors, forces, moments. A lot of these general topics we'll dive into a little bit more later. We have a tentative course schedule here. It's a little bit strange because usually we have 4 weeks before Christmas, but this quarter we only have 3 weeks just because Thanksgiving was so late. But I do want to squeeze in an exam before the break, and I want to have 3 exams for the class. Generally, that's because sometimes people just have bad performance on one exam because they, whatever reason, aren't so great on one particular topic. Okay, if you spread it over 3-4 exams, then it's not hurting you as much. All right. So first exam is actually going to be Friday right before break, and so that's gives us 2.5 weeks to prep for that first exam. Okay. So you can see the topics here that we're going to dive in on. Introduction mechanics, forces and vector math. Hopefully you've seen at least a little bit of vector math at this point, maybe in your physics class. 2D particle equilibrium, 3D vectors, 3D particle equilibrium, all these topics leading up to the first test. So we'll dive in on that in the weeks to come. Then you can sort of see what's going to be happening in the future after Christmas break, all this sort of stuff. Not going to go over it right now. You can sort of take a look on your own time. And maybe these things don't even make sense to you right now. You're like, what the heck is internal force and moment? I don't know. Well, it will become clear to you eventually. All right. Course grading. I'm as lenient with the course grading as the department allows me to be. Okay. So I can't even go any lower than this. So I'm basically like traditional 90 is 100 is an A, 80 to 87 is a B, 87 to 90 is an AB, etc. Okay. We're going to have 3 exams in this class. You're going to have simulation assignments, probably 3 of them, so each worth 5% of the grade. Final exam worth 30%, and your homeworks are going to be worth 10%. So you have homeworks for this class. I will write them, so good luck finding them on the internet. I promise you they do not exist. I will write them, so keep you honest in doing your homeworks. All right. There was bound to be some objections about grades sometime. If you have an objection about a grade, you got to submit something to me in writing. Email is an acceptable form of writing. I just need a documented case. Okay, so send me an email saying, I believe I should get more points back because of this, and you were a jerk and too mean to me for a little negative sign. Okay, maybe I'll give you points back. Maybe. Okay. Submit it in writing, and I'll make a decision. And if you still don't agree with me, you can appeal to the chair. All right. Like I said, simulcasted lectures from this classroom. Free to attend in-person lectures when your block is eligible, though based on attendance today, you can probably come anytime you want. I don't think it'll be a problem. All right. Lectures recorded and uploaded to my YouTube page. Again, the link to that YouTube page is in Canvas right now. Would be nice if you all attended lectures. I really encourage that just because live lectures are probably the best and most accountable you can be for learning the material at the time. If you just kind of slack off and say, oh, I'll watch that lecture later, you're not going to watch the lecture. Let's be honest. Come on. Come at the time. I'll be here. You should be here. It's just the best way to learn, I promise. Question? Nope, no question. All right. Can you please mute your mic? Thank you. I'll mostly use the writing pad to lecture. So I do have kind of like this free whiteboard here that I'm mostly going to use to write on and lecture. So, you can see in the classroom up there on the board exactly what people in Microsoft Teams can see. So this is what I'm going to use to lecture mostly. And I'll supplement with some of the material from the lecture notes. So if you want to look at the lecture notes as I go, that's fine. If you want to copy by hand as I go, that's also fine. Should be able to keep up in both situations. All right. Finally, simulation projects using MATLAB will be assigned periodically. Probably have 3 during the quarter. This isn't, a MATLAB class. I'm not going to be asking you to do like crazy, insane things in MATLAB that you didn't learn in 190. But you have to know how to use MATLAB, right? I expect you to know how to do like multiplication and addition in MATLAB. All right. I expect you to know how to use like the dot. All right. This is not really like that difficult things. You should know how to sort of do that stuff. All right. Continuing, homeworks. Workout problems. No like multiple choice homework questions. Okay. Real legitimate engineering homework here. I'm going to give you the final answer on the homework. So you'll see a prompt and then I'll give you what the answer should be. It's up to you to do the work to show me and to get there. All right. So I give you the answer so that you can understand and work through a problem if you're coming on the wrong answer, right? It's not useful or not helpful for you to learn. If you work through the problem, you get it wrong, you turn it in, and then you just don't even know that you messed up, right? So I give you the answer for a reason. So work through it and try to match my answer. If you're not matching my answers, come to office hours every day, 8 to 9:30 a.m. All right. Continuing. Sit on Canvas, corresponding due date, usually about a week after. You'll probably see a homework posted tomorrow. All right. That'll be your first assignment. Hand it in virtually. Hand them in to me by email. You can email me anytime up to the due date. PDF format preferred. Please don't just send me like a bunch of pictures. That's really annoying. Okay. Put it in a Word document, save it as a PDF, and send it to me. The way I deal with homework, I'll grade one problem. It's going to be the basis for 80% of the grade. So I'm going to pick one at random, usually out of a hat or out of an Excel sheet. I'll just like do a random number generator and pick one. All right. That'll be worth 80% of the grade. And then the other problems, I'll just scan to make sure you did them. And that'll be worth 20% of the grade. All right. Please be nice with your formatting. In the virtual world, you know, you can get away with a little bit more, but try to be neat with your homeworks, I'll say. All right. Usually there's like a handful of people in this 2001 class, this is like your first engineering class, who try to do all their work in like one little page, right? Like, okay, engineers, if you look at engineering drawings, they don't fit all their drawings into like one little box in the upper right corner of the page, okay? Like use a big piece of paper and like make a nice big drawing and don't try to squeeze it in one tiny little area, right? Like you can use 3 pieces of paper, all right? It's not gonna kill the world, all right? So now's the time to graduate to using large amounts of space to communicate your ideas clearly. All right. So there you go. All right. Continuing. Exams. Exams are going to be held virtually. So don't come to class on exams days. I'm going to ask you to turn your video camera on and point it at your workspace, but keep your microphone muted. I will have open everything for tests. Okay, you can look at notes, you can look at your calculator, you can use MATLAB, you can use Wolfram, you can use the internet, you can use whatever you want. All right. There's no way that I can police you not doing it if we have a virtual format. I can't do it. So I'm just going to say you can use whatever you want, but the test, you got to know what you're doing walking into it or you're going to be in trouble. All right. I'll just tell you that. So 3 in-class exams, 1 final. Virtually on Teams, do it by hand and then email it to me. Usually in a 50-minute period. I'll give you 45 minutes to do it and 15 minutes to send it to me by email. It's plenty of time to take pictures of your stuff, put it in a file and send it to me. 15 minutes? Come on. Just like the technology. You guys are like born with technology, right? So should be no problem. I've not had issues in the past, so we'll do it that way. Calculators allowed, obviously. It's going to be open everything. No makeup exams for unexcused absences. If you have some excuse where you can't make it on time, please tell me in advance. Please in advance. Okay. The final is established by the registrar. I don't know when that final will be. Please do not make plans to like go somewhere on Valentine's Day and never return. Okay. You got to be here for the final, right? So makeup finals really are not possible. I think this class typically has a common final, but since this is not the typical time slot offering of this class, I don't think that the final will be common. So that just means that the final is common for every single section of the class. I know in the fall term when 2001 is typically offered, there is usually a common final. I don't know if they did last quarter or not. I don't think they did actually last quarter. So I think the final is actually going to be at my discretion, which may or may not be a good thing for you guys. Yeah. Okay. So that's that. Cheating and dishonesty, just don't do it. If I see you cheat on an exam, you're out of the class. Okay. Like if I can see that you're doing it on video, I will kick you out and that's it. I mean, you can appeal, but you're probably going to lose. So don't cheat. All right. Same thing for computer code. If you hand in a MATLAB script that looks like exactly like someone else's with a bunch of variables changed, you're out. Okay. I don't mess around. I've written up people and kicked people out of classes before. All right. I'm not messing around with this one. Don't do it. All right. I don't mind if you work on some homeworks with other people. I know that's sort of social aspect of like doing homework is fine. So if you have very similar workout strategies for homework that someone else does, it's fine. As long as you're just doing your own work, that's okay. But if you just like copy paste someone else's code and hand it in, you're out. Okay, that's it. All right, last thing, final comments. Like I said, this is probably like your first foray into engineering classes where you're starting to see drawings. It's like kind of an exciting time. I think it's really a time where you sit back and you say, is engineering really for me, right? I see all these forces. I'm looking at real life drawings. I'm analyzing real structures, and sort of doing mathematical analysis, and it's really the time to decide, do I have the visualization capability to do this? Do I have the math prowess to do this and be an engineer? And people that do well in this class usually go on to be very successful engineers. So please, I want to help you through this. I know it's a different style of class because you're seeing engineering drawings, you're seeing forces, you're seeing math and kind of how the world works. It's different than like a calculus class where you just do 50 integrals and hand it into your teacher. All right, you're actually doing like analysis on real stuff now. And it's very exciting. I think it's great. I think back to when I took statics and it was like, man, this is awesome. Right. So I hope that I can instill that in you guys as well, bring it home to you guys. All right, a couple comments about COVID. I'm offering this class in a manner such that you do not have to have any physical in-person component of this class if you don't want to. You can take my class entirely online, right? All the lectures are going to be broadcast via Teams. Everything will be recorded. You can hand everything in online. You can do everything at home. So, if you prefer to do that, that's fine. I'm not going to hold it against you. I would just say, please be careful about the whole situation, wear masks, be safe, all that sort of stuff. There's lots of resources with the Dean of Students office that you can go to if you're having issues, if you think you have symptoms and you want to get tested, fine. If it's interrupting your ability to do something in my class, like let's say you're sick and really can't take the test because you're struggling with your physical health, please let me know and we can work something out, okay? If I don't know though, I can't really help you. Okay, so I have this little extra ditty in here. Please be safe. That's all I'll say. Any questions about the syllabus? In-person, online audience, ask in the chat or ask with your microphone while I do the moonwalk. Just kidding. They can't see. Okay, if there's no questions, then let's go on to the introduction of material. So I'm just going to talk over these first introduction to mechanics slides. This will be the last time I talk over a set of slides. I don't like talking over slides generally, but for this introduction to mechanics, we got some kind of cool pictures. Like talk over that I'm not generally going to ask you or test you on. I just think it's good information for you guys to know. Okay, so nothing you necessarily see today is going to be not any test per se. It's just more or less, let's talk about what mechanics is and what we're going to sort of learn about this quarter. So let's do that. Okay, here we are. Introduction to mechanics. This is a tensegrity structure. Anyone seen a tensegrity structure before? Yes, we got some head nods. We got a head shake. No. So a tensegrity structure is one where you have members in both compression and tension that's self-sustaining. So what you kind of see here, and it's kind of cool, is that you see some of these wires that are kind of like connected from post to post. And these wires here are holding tension. All of these wires are holding tension. Typically, wires don't hold compression very well. And all these steel members here are holding compression. And the compression that are in the bars and the tension that's in the ropes kind of hold everything together to give you this like three-dimensional structure that kind of self-supports itself with all the tension and compression that's inside the piece. It's pretty cool. There's some people that have like made furniture out of this as well, and it's kind of a cool engineering thing when you know about all the forces that are sort of being transferred inside of that structure and how those things are interacting. So I particularly like this, and this tensegrity structure is actually at the Milwaukee Art Museum. So I took this picture myself, and I think this is a pretty cool structure because it is static, right? It's not moving. It has a bunch of forces on it that are sort of interacting with itself to give you this like artistic rendering of something that's self-supporting. And it's kind of cool and a nice introduction to sort of what we're going to be learning. And that's about forces that are sort of inside objects that are not moving around. So that's kind of the basis for like what is mechanics, right? And when we talk about mechanics, you've probably heard that word thrown around a lot, right? Like you have mechanics 1 and mechanics 2 and fluid mechanics and blah, 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 okay? And mechanics is like, it's this very broad word, but maybe you could put like some actual definition to it. And what it generally is defined at is the science that describes and predicts conditions of rest or motion of bodies under action of forces. And we sort of split it into three sort of areas generally as we progress with our learning of mechanics. The first area is rigid bodies, and rigid bodies are more or less bodies that don't deform significantly under the loads that are applied. All right. And that's mostly what we're going to deal with in this particular class. Okay, that's why I've highlighted it in red. You also have deformable bodies, and I put Jello there as a nice like example where it doesn't take a lot of force to deform this thing substantially. And so doing an analysis on this with an idea of it not moving or it being static is not really reasonable. And so something that is deformable is reserved for a higher level mechanics class, which you're going to study in things like 2004 and 3005. All right, so you'll see those coming if you keep on the mechanics path. Then finally, fluids, fluid mechanics. Obviously, these are bodies that will deform when you put load on them, right? So fluids are kind of their own special, unique category, and you'll study fluid mechanics later in your ME curriculum, you know, mid-junior, late junior year, something like that. It's a little bit more complicated. But for now, we look at first rigid bodies. And rigid bodies, like I said, split into sort of like two categories. There's statics, which is the mechanics of bodies at rest, and there's dynamics, which is the mechanics of rigid bodies in motion. And so you'll see this in 2001 as your statics class, and then 2002, 2003 are like your dynamics classes. All right, so these mechanics sequence that you sort of take when you're a sophomore. You'll start with statics, bodies at rest, and then dynamics, which is like 2002 and 2003. So obviously this is your 2001 class, so we're going to focus on mechanics of bodies at rest. So these are undeformable rigid bodies that have some loads on them that we're going to analyze mathematically. And the basis of this class generally is that the sum of the forces that are acting on some structure are going to be equal to 0 because this object is not moving. So if you've seen mechanics a little bit in the past, something like this truss structure with a series of loads on it and how this structure is responding to external loads is something that we're going to dive in on and analyze. So here's a little bit more detail on what's happening with this truss structure. And don't worry if this is freaking you out. We're gonna talk about, and you'll have plenty of chances to make drawings like this as we go through this class. All right. Then after this class, you'll move on to actual motion of these rigid bodies, where now the sum of the forces acting on the body are not equal to 0, but they're equal to some mass times acceleration. And this is where we're hopefully ultimately trying to get you with mechanics, is basically using Newton's second law, force equals mass times acceleration. That Newton guy, man, he knew a thing or two, right? So that's what you're going to study in 2002 and 2003. So I just want you to see where your mechanics curriculum is sort of like fitting in on the grand scheme of things. All right. Now here are 6 principles of mechanics, the Newtonian mechanics. And this comes right from your book. And I'll sort of talk over these, and maybe I agree or disagree with your book assigning these as the 6 principles, but I'll go over them and cover them anyways. Okay, so the 6 principal laws, parallelogram law for addition of forces. So 2 forces on a particle can be replaced by a single resultant force. We'll actually see that tomorrow. Okay, so that's kind of the first thing that we're going to go over. Principle of transmissibility, that is that conditions of equilibrium in motion remain unchanged if a force acting on a point is replaced by a force of the same magnitude and direction at a different point. What do I mean by that? Okay, it's just a lot of like gobbledygook, blah, 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 blah. Okay, you can replace 2 forces with one if that one force has the same general line of action. Okay, so this is this basis of like you can add 2 forces on a structure together, giving you 1 force, and those 2 different systems have basically the same outcome. Okay, Newton's first law, second law, third law. These are the big dogs. All right. It seems silly that we're basing a whole field of study, including fluids and solids and deformable bodies and etc., on these 3 laws. But man, I'm telling you, that Newton, he was ahead of his time, right? Standing on the shoulders of giants. But here's the trick: he was the giant. All right. Newton's first law: the resultant force acting on a particle is 0. Particle remains at rest or moving with constant speed in a straight line. So objects in motion stay in motion unless acted upon by outside forces. You've probably heard that before. And will be something we discuss in this class. Newton's second law: resultant force acting on a particle is not 0. That particle has an acceleration. Right? So we're not going to get into that really in this class. F equals ma comes later in your dynamics class. In this class, we're going to focus on F equals 0. Right? Newton's third law: for every action, there is an equal and opposite reaction. So think about jumping off the canoe. All right, you're going one way, the canoe's going the other way. All right, it's the classic example. Newton's law of gravitation. This is one maybe you've seen in your physics class: gravitational constant g times m1, m2, the masses of the 2 objects, inversely related to the square of the distance between them, gives you some force of attraction between them. So I'm attracted to all of you, even you sitting at home, by g m1, m2 over r squared. Right now, we have a gravitational constant between us. Me and you, me and you, me and that wall, me and the earth, obviously. Me and all of you sitting at home. we have a gravitational pull towards each other inversely related to the distance between us multiplied by our masses multiplied by the gravitational constant g. So that's another theorem that Newton came up with. Again, pretty smart guy. Units, I put these here for your reference later. We'll do a lot of like unit conversions in this class just because it's something that we need to take care of in this class. So you can use this for reference later. Again, these slides are available on Canvas. You can go ahead and take a look at them. But a lot of things that you'll see here, unit conversions between US units and imperial units and metric units. Unfortunately, we live in the US and we have a really flowing unit system here. The more and more you get into the depths of science, if you come, get a PhD in engineering or even a master's degree, then more and more you will start to use metric units. And usually if you're working in like a foundry locally, a small foundry in the United States, or if you're working on building cars, or maybe even in the military in a lot of applications, you're going to be working with English units a lot. So unfortunately in the US, we can't really agree on a system all that well, even though most of the systems that we use are English units. You do have to be comfortable working in both unit types, and we'll have problems with both metric units and English units in this class. So you're going to have to be comfortable with slugs, sadly. All right. SI prefixes, we'll use some of these probably into like I would say the micro to maybe mega range. We'll definitely talk about meganewtons at some point. Micronewtons, maybe not, but micrometers probably. All right. Converting between units, I've given you your standard chemistry 101 type unit conversion example here. This is kind of how I like to see it in the homeworks if you're going to do it. Obviously, you write the original quantity, some conversion factors, and you can convert your units appropriately. Here's an example. You guys have done this in chemistry, yes? Can I get some head nods? Yeah, okay, good. So here's an example of that. Hopefully we know all that. And as I said, you're starting to move into your engineering problem-solving classes now. Maybe you've had little pep talks about solving problems in the past before, and maybe you haven't, but when you're solving problems and when you're presenting me with an answer or a solution to a problem, if it doesn't make sense, I'm going to be irritated. Okay. So if you tell me that a little paperclip can hold up 50,000 meganewtons, I'm going to be mad. All right. It doesn't make any sense. Right. So go through some realistic check on your work to make sure that it makes sense. All right. And if you're stuck on a problem, you might want to reevaluate whether or not you know all of the information that you're reading. So sometimes you'll come across like, what is the internal moment in this structure? And that's something you're going to solve for. Well, if you don't know what a moment is, you're not going to do very well. Okay. So you have to know your vocabulary as well. Do I know all the definitions of the words? Do I know my knowns and my unknowns, right? Engineering is all about bridging things you know and things you want to know, okay? So I have all this information here and I want to know all this information. How do I go across that void, all right? What formula technique bridges that gap, right? Are my units correct? Does my answer make sense? You don't have a paperclip with 50,000 newtons on it, okay? It doesn't make any sense, all right? Can I plug this back into check? That's also another thing to do. Can I attack this problem a different way to check my answer, etc. Okay, so that'll be it for today. Cut it short, just a half-hour lecture today. An introduction to mechanics. I hope you guys are excited to learn about some statics. It's really an interesting class, your first foray into engineering, and I'm excited to tackle it with you. All right, so thanks for coming today, and we'll see you tomorrow. See you tomorrow. Yeah, see you. Gotta have some passion, gotta have some fire.